Section 3.2, the derivative as a function. In this section, we're going to go over some terminology associated with the slope of tangent lines. First, we're going to let f of x be a function. We say that f is differentiable at x equals a if f prime of a exists. Recall, f prime of a is the slope of the tangent line of f of x at x equals a. Just like with continuity, we can define differentiability over an entire interval. We say f of x is differentiable on an open interval ab if f is differentiable at x equals c for every c in the interval ab. Now, we can also say that f is non-differentiable at a point x equals a if f prime of a does not exist. Next, we're going to determine if the following functions are differentiable at the indicated point. So first, f of x equals x squared at a equals 2. To determine if a function is differentiable at the point, by the definition of differentiability, we want to see if f prime of 2 exists. This would be the limit as x approaches 2 of f of x minus f of 2 all over x minus 2. F of x is x squared. F of 2 is 2 squared or 4. So we're taking the limit as x approaches 2 of x squared minus 4 over x minus 2. Since this is rational and we're going to have 0 over 0 if we try to plug in directly, we'll factor the numerator, then cancel out common factors. So we get that our limit would equal the limit as x approaches 2 of x plus 2. Now use direct sub, and we get that the limit is 4. So going back to the original question, is f of x differentiable at 2? Yes, f of x is differentiable at 2, and that's because f prime of 2 existed. Next, we're going to determine if g of x is differentiable at a equals 0, which means we're trying to determine if g prime of 0 exists, which means we're trying to determine if the limit as x approaches 0 of g of x minus g of 0 over x minus 0 exists or not. X minus 0 is x. To evaluate g of 0, we would use the first equation where x is greater than or equal to 0, which means we would get negative 1 as the value of g of 0. The problem is g of x. Around x equals 0, g of x could behave as either one of the two equations, the x minus 1 or the 2x minus 2. So for that reason, in order to decide what g of x will be, we have to consider the left and the right-hand limits. First, we'll evaluate the limit as x approaches 0 from the right. From the right of 0, our g of x would be x minus 1. That's because when we're to the right of 0, we're working with values slightly bigger than 0. Now we can simplify. When we simplify the numerator, we get x, and then we can cancel out the x's, and we get 1. The limit as x approaches 0 from the right of 1 would just be 1. Now for 0 to the left, since we're approaching 0 from the left, we're working with values of x smaller than 0, which means we would plug into the second equation. So g of x will be equal to 2x minus 2. Now we can simplify, and we get the limit as x approaches 0 from the left of 2x minus 1 over x. If we try direct substitution, we get negative 1 over 0, which is an indicator that we'll be approaching either infinity or negative infinity. Since I only care about whether or not the limit exists, I don't have to determine which infinity I would approach, but this is enough to conclude that my f prime of 0 does not exist, which means our function g of x is non-differentiable at a equals 0. Next, we're going to determine if h of x equals the cube root of x is differentiable at a equals 0. So here, we're trying to evaluate h prime of 0, which means we're trying to see if the limit as x approaches 0 of h of x minus h of 0 all over x minus 0 exists. H of x is the cube root of x. H of 0 is 0. Anything minus 0 is itself. And we get the limit as x approaches 0, the cube root of x over x. So a lot of times in calculus, radicals can be rather problematic, especially for cube roots, fourth roots, or higher. In this situation here, in order to help us resolve the 0 over 0 indeterminate form, which is what we would get if we tried direct substitution, it helps to rewrite our radical, in this case the cube root of x, as a rational exponent, which would be x to the 1/3. This is because, if you recall, the way we rewrite radicals as rational exponents is that the nth root of x is equal to x to the 1 over n. By rewriting our cube root as an x to the 1/3 power, we can now use exponent properties to simplify. And when we do use those exponent properties, we get that we're taking the limit as x approaches 0 of 1 over x to the 2/3 through direct substitution. This would be 1 over 0, which means if we broke it up the left or right-hand limits, we would wind up with infinity or negative infinity. So our h prime of 0 does not exist, which means our function is non-differentiable at a equals 0. Next, we'll see if capital F of x, which is the absolute value of x, is differentiable or not at a equals 0, which means we're trying to determine if f prime of 0 exists. Setting up our definition for f prime of x is the absolute value of x, while f of 0 is 0, so we know that the numerator would just be absolute value of x. The denominator would be x. The issue in this problem is if I plug in 0 through direct substitution, I still get 0 over 0. However, how do I simplify this absolute value of x over x to resolve the 0 over 0 indeterminate form? It's not rational, so factoring won't help. There are no radicals, so rationalizing will not help. There's no complex fractions, so clearing complex fractions won't help. The common strategy when working with absolute values in calculus is that we observe the absolute value function as a piecewise function. The absolute value of x is x if x is greater than or equal to 0, or it's negative x if x is less than 0. This is because whenever we try to take the absolute value of a positive number, it remains unchanged. So what we put in, we get out when x is greater than or equal to 0, which is why the absolute value of x would equal x if x is greater than or equal to 0. However, if we plug in negative numbers into the absolute value, it outputs a positive number, precisely the opposite of what we put in. So the absolute value of x would equal negative x, and the negative is to denote the sign change from a negative value to a positive value, and this occurs when x is negative or less than 0. So looking at this as a piecewise function, we want to consider the one-sided limits. When x approaches 0 from the right, we're dealing with positive values or values bigger than 0, which means absolute value of x will be x. Now, since we got rid of the absolute values, we can reduce, and when we do, we get that the limit is 1. For the left-hand limit, we're dealing with values of x that are negative or smaller than 0. According to the piecewise definition, the absolute value of x will equal negative x. Then we can reduce, and we get that the left-hand limit is negative 1. So the right-hand limit is 1, while the left-hand limit is negative 1. So f of x is not differentiable at a equals 0. If we were looking at a graph of a function, how can we determine whether or not a function is differentiable at a point or not? The first way to answer this question is through the following theorem. We'll let f of x be a function. If f is differentiable at x equals a, then f is continuous at x equals a. We have to be careful interpreting this theorem. What this theorem communicates to us is that differentiability is a stronger condition than continuity. And what we mean by that is if a function is differentiable, then f is definitely continuous. That is what the theorem clearly states. However, a function can be continuous at a point, but not differentiable. We can think of differentiability as continuity plus the added feature of the slope of the tangent line at that point existing. So with this theorem and a few other observations, we can conclude that a function is going to be non-differentiable at a point if any one of the following characteristics occur. First, if our point is discontinuous. In order to be differentiable, we must be continuous. So if a function is discontinuous at a point, then it cannot be differentiable. And we've seen what discontinuities look like in the previous unit. The other characteristics is first, anything that forms a sharp point, such as cusps, which we see here, or corners, which we see here. Sharp points are usually formed when, if we break the definition of the slope of the tangent line into left and right-hand limits, both the left-hand and right-hand limits are not approaching the same value or not approaching the same infinity. This results in a sharp point being formed, as we see in these two images. The third characteristic is what we call a vertical tangent line. If we take a look at the graph on the right, here at x equals 0, we can form a series of secant lines. Notice how each secant line we draw is getting steeper and steeper as these green points are getting closer and closer to the blue point. That would indicate that as our green points approach the blue point at x equals 0, our secant lines are approaching a tangent line that is vertical. We call these kind of lines vertical tangent lines. They occur when our derivative approaches positive infinity or negative infinity. And both the left and the right-hand limits will approach the same infinity, whether both approaching positive infinity or both approaching negative infinity. Vertical tangents can be a little bit harder to spot, but if you observe the graph of the example we have provided, notice how as we trace, we can see that there's this really quick jump upwards where it almost looks like the graph itself is becoming a vertical line. That is the typical indicator of a vertical tangent line. Next, we're going to let f of x be a function defined by the graph below. We're going to determine where f of x is differentiable and where f of x is not differentiable. Just like with continuity, it is easier to determine where a function is not differentiable because usually that occurs at a few finite points, and then use that information to determine where f of x is differentiable. Scanning the graph from left to right. When we're scanning the graph, we want to look for any discontinuities or vertical tangents or sharp corners. Scanning the graph, we first see a discontinuity at -1, so x equals -1 is a point of discontinuity and therefore a point of non-differentiability. Continuing the scan, here at x equals 0, we have a sharp corner, so x equals 0 is where f of x is non-differentiable as well. Now at x equals 1, which is a little bit more subtle, notice how we have this very sharp, almost vertical bend in our graph. That indicates that we would have a vertical tangent at x equals 1, so f of x is non-differentiable at x equals 1. At x equals 2, we don't quite have as sharp of a corner as we do for x equals 0, but it is still a corner nonetheless that is relatively sharp compared to the rest of the graph. So x equals 2 is also a point where our function is not differentiable. Now that we know everywhere where the function is not differentiable, where is our function differentiable? Well, that would be every other location other than those 4 points, which would be negative infinity to -1, -1 to 0, 0 to 1, 1 to 2, and 2 to infinity. Before our next topic of discussion for this section, we're going to let f of x equal x squared, and we're going to find the values of f prime of 2, f prime of 3, and f prime of 4. F prime of 2, we actually found in example 1. In example 1, we found that it was equal to 4. Now we'll figure out f prime of 3 by using the definition. That is equal to the limit as x approaches 3 of f of x minus f of 3 all over x minus 3. F of x is x squared. 3 squared is 9. So we have the limit as x approaches 3 of x squared minus 9 over x minus 3, which we will simplify. And when we do, we get the limit as x approaches 3 of x plus 3, which is 6 through direct substitution. Now for f prime of 4, which will be the limit as x approaches 4 of f of x minus f of 4 over x minus 4. F of x is still x squared. F of 4 is 4 squared, which is 16. And just like above, we're going to factor and simplify. And after factoring and canceling out common factors, we have the limit as x approaches 4 of x plus 4, which through direct substitution will equal 8. Notice that in this problem, we are pretty much doing the same work over and over again. And it's pretty tedious with a lot of work. What we're going to do is talk about a quicker approach to this problem, where if we're working with the same function, but want to find the tangent line of our function at multiple different points, we won't have to do as much work repetitiously. To help us make problems like example 3 faster, we're going to define a function that represents the slope of the tangent line of our function at a given point x. And this function is going to be referred to as the derivative. We're first going to learn the limit definition of the derivative. Here, we're going to let f of x be a function, then the function f prime of x, which equals the limit as h approaches 0 of x plus h minus f of x all over h, is the derivative of f of x. Notice that the definition uses the limit of the difference quotient, which was one of the definitions of the slope of the tangent line that we discussed last section. The reason why we're using the difference quotient variation as opposed to the other variation that we were using in the previous example is because the variation we were using in the previous example is great when we're trying to find the derivative or the slope of the tangent line at a single point. But when we're looking at the derivative as a function, it is easier to use the difference quotient because the difference quotient has a lot more cancellation involved with the f of x plus h minus f of x, and it is easier to simplify to try to cancel out the h in the denominator rather than the x minus a in the other variation. As far as representation goes, f prime of x is just a function that represents the slope of the tangent line of f at x. The domain of our derivative f prime of x is where f itself is differentiable. So for our next example, we're going to let f of x equal x cubed, and we're going to find f prime of x using the limit definition. Now, because our definition is just the limit of the difference quotient, we're going to evaluate our difference quotient first and then take the limit as h approaches 0. The first step of finding our difference quotient is we want to find f of x plus h, which here would be x plus h cubed. If we expand this using our special formulas, more specifically a plus b cubed is equal to a cubed plus 3a squared b plus 3ab squared plus b cubed. X plus h cubed would expand to x cubed plus 3x squared h plus 3xh squared plus h cubed. One thing to note, though, is that if you don't remember the formula, the alternative is we can write x plus h cubed as x plus h times x plus h times x plus h and FOIL two factors at a time. Now for step 2 of the difference quotient, we're going to simplify the numerator, obtaining the f of x plus h minus f of x. To do that here, we're going to take our f of x plus h that we obtained in step 1, our original function, and we're going to subtract, which was x cubed. The parentheses were placed to emphasize that anytime we're replacing something with an expression, we should put parentheses around it. However, around the f of x plus h, we do not need the parentheses since there's nothing to distribute. So we'll drop those parentheses. Then we can collect our like terms, and we can see that the x cubes cancel. And we're left with 3x squared h plus 3h squared plus h cubed. To finish finding our difference quotient, we will divide our result from step 2 by h. Remember, when we're trying to simplify the difference quotient, our goal is to try to cancel out the h in the denominator. To do that, we can observe that in the numerator, h is a common factor. So we can factor out h, and from there, we can see the h's cancel. Now that we have our difference quotient simplified, our f prime of x will be the limit as h approaches 0 of our difference quotient. Keep in mind that h is what's approaching 0. So when we use direct substitution, we are replacing h with 0. Since anything times 0 is 0, then the derivative of x cubed is 3x squared. Now that I know that f prime of x is 3x squared, the next parts are easy to figure out. To figure out f prime of 2, we're just going to plug 2 into our derivative. So f prime of 2 would equal 3 times 2 squared, which is 12. F prime of 3 is 3 times 3 squared, which is 27. And f prime of 4 is 3 times 4 squared, which is 48. So notice how we did all of the simplifying at the beginning, finding our derivative. And from there, all we just had to do is plug in various values of x to find our derivative at various points, or the slope of tangent lines at various points. We're going to find the derivative of each of the following functions using the limit definition. Then we're going to determine where each function is differentiable. We'll start off with f of x equals x squared minus 3x plus 4. Going through and evaluating our difference quotient. First, finding the f of x plus h, which means we're replacing x with x plus h. So we have x plus h squared minus 3 times x plus h plus 4. Now we'll proceed to expand. X plus h squared becomes x squared plus 2xh plus h squared, distribute in negative 3, and bring down to plus 4. Then we would collect like terms, but here there are no like terms to collect, so step 1 is complete. Going to step 2, we'll find the f of x plus h minus f of x, meaning we're taking our result from step 1 and subtracting the original function. And when we subtract the two, remember to put parentheses around the two expressions. In the first set of parentheses, we can drop them since there's nothing to distribute, but in the second set, we do have to distribute in negative 1. After that, we can collect our like terms, and we'll see quite a few terms cancel. The x squareds cancel, the 3x's cancel, the 4's cancel. And we have 2xh plus h squared minus 3h as the f of x plus h minus f of x. One thing to note, whenever our original function is a polynomial, after step 2, our resulting expression should have h as a common factor amongst its terms. If your function is a polynomial, and your f of x plus h minus f of x does not have h as a common factor, then that means you made an error somewhere in calculation and should go back and retry the problem. It may be difficult to try to backtrack where you've made your first error. I'm going to combine step 3 and step 4 from our previous example, and we're going to jump straight to the f prime of x, where we're going to take the limit of our difference quotient. That's because we already know what our numerator is, so all we would have to do is place our numerator, do the division, and then take the limit. factor out h in the numerator. Now we can see that the h's cancel, specifically the h I want to cancel out in the process of simplifying the difference quotient. So we'll take the limit as h approaches 0 of 2x plus h squared minus 3. Remember, since h is approaching 0, then when we direct sub, we only replace h with 0. And now when we simplify, we get 2x minus 3. So the derivative of f of x is 2x minus 3. Next, we're going to determine where f of x is differentiable. F of x is differentiable on the domain of f prime of x. We do have to be very careful, though, with context. Looking at f prime of x, its domain is negative infinity to infinity. But we also have to be careful. F prime of x is only defined wherever f of x is differentiable, meaning the limit of the difference quotient has to exist. One thing we have to be careful of is removable discontinuities. Through this limit process, since we're not plugging in a specific value for x, we may be able to reduce our expressions to where we remove those discontinuities of our original function. So it's not enough just to see where f prime as a function is defined, but we also want to check to see if there's any removable discontinuities. Since f of x is a polynomial, there are no removable discontinuities since there are no discontinuities. We're going to see the importance of why we need to check to make sure f of x, our original function, does not have any removable discontinuities in the next example. However, as for the question of where is f of x differentiable, f of x is differentiable on the interval negative infinity to infinity. Next, we'll find the derivative of g of x, which is 3 times x minus 1 all over x minus 1 times x plus 1. We'll begin with step 1, finding g of x plus h. After replacing x with x plus h in g of x, we get 3 times x plus h minus 1 all over x plus h minus 1 times x plus h plus 1. Observe that x plus h minus 1 is a common factor in the numerator and denominator. So we'll cancel them out, and we're left with 3 over x plus h plus 1. Now that we have g of x plus h, we'll move to step 2, finding g of x plus h minus g of x. So we'll take our results from step 1 and subtract our original function. Notice that in our original function, we have x minus 1 as a common factor, so we'll cancel them out. Now from there, to subtract fractions or rational expressions, we do need a common denominator. If we take a look at the first fraction, we do not have x plus 1 as a factor of the denominator, which we do see as a factor of the denominator of the second fraction. So we'll multiply top and bottom by x plus 1. In our second fraction, we have x plus 1 as a factor, but not x plus 1 plus h. So we'll multiply top and bottom by x plus h plus 1. Since we have a common denominator, we can subtract the numerators while keeping the denominator the same. So we're left with 3 times the quantity x plus 1 minus 3 times the quantity of x plus h plus 1 all over x plus h plus 1 times x plus 1. Since we're trying to simplify the difference quotient with a rational expression, we should try to have the numerator and denominator factored to make it easier to cancel out with the h in the denominator of the difference quotient. So we'll keep the denominator factored, but in the numerator, I do want to expand to see if I can factor it. We'll distribute the 3 into the first set of parentheses and the negative 3 into the second set of parentheses. And when we do, our numerator becomes 3x plus 3 minus 3x minus 3 minus 1. And again, we'll keep our denominator factored. Now we'll simplify the numerator. We see that the 3x's cancel, and we see the 3's cancel. And we're left with negative 3h all over x plus h plus 1 times x plus 1. Now we'll find our g prime of x, which would be the limit as h approaches 0 of our difference quotient. Since we've already found the g of x plus h minus g of x, we just have to divide it by h. Since we're dividing our g of x plus h minus g of x by h, we're going to treat the h as h over 1. And since we're dividing fractions, that is the same as multiplying by the reciprocal of the second fraction. So instead of dividing by h, we'll multiply by 1 over h. Then we see the h's cancel, and we have the limit as h approaches 0 of negative 3 over x plus h plus 1 times x plus 1. Now we'll do the direct sub, replacing h with 0, and we have negative 3 times x plus 0 plus 1 times x plus 1. X plus 0 plus 1 is the same as x plus 1, and x plus 1 times x plus 1 is x plus 1 squared. So g prime of x is negative 3 over x plus 1 squared. Now we'll determine where g of x is differentiable, meaning we need to find the domain of g prime of x. This is where we have to be very careful. With the negative 3 over x plus 1 squared, it is very tempting to just look at the natural domain and say that the domain of g prime of x is negative infinity to negative 1, union negative 1 to infinity, and then g of x would be differentiable on these intervals. However, the reason why this would be incorrect is g prime of x came from the limit of the difference quotient. So it's not enough to just look at the equation. Another important aspect we need to consider is the removable discontinuities. G of x is discontinuous at x equals 1 and negative 1, since g of x would be undefined. However, if you try to classify each continuity, x equals 1 is a removable discontinuity. And through our work through the limit process here, we were able to remove that discontinuity, which would be a value where our limit would not exist. And that would be a location where if I just tried to find the limit of our difference quotient at that specific point and only that point, the limit would not exist. So for that reason, it's incorrect to say that g prime of x has a domain of negative infinity to negative 1, union negative 1 to infinity. We also have to exclude 1. Even though, yes, I can plug 1 into the equation for g prime, technically speaking, g prime of 1 does not exist because g of x is discontinuous at x equals 1. The correct domain of g prime of x is negative infinity to negative 1, union negative 1 to 1, 1 to infinity. So g of x is only differentiable on the intervals negative infinity to negative 1, negative 1 to 1, and 1 to infinity. So make sure we are very careful paying attention to removable discontinuities when we're looking at the derivative of a function to determine where a function is differentiable or not. Next, we're going to find the derivative of f of x, which equals the square root of 4x minus 1 plus 1. we'll start by finding f of x plus h, which would be the square root of 4 times the quantity x plus h minus 1 plus 1. Then distribute into 4, and we get the square root of 4x plus 4h minus 1 plus 1. Now we'll take our result from step 1 and subtract f of x. And we get the square root of 4x plus 4h minus 1 plus 1 minus the square root of 4x minus 1 plus 1. We'll simplify by dropping the parentheses, by distributing where we need to, and then collecting like terms. And we get the square root of 4x plus 4h minus 1 minus the square root of 4x minus 1. Now we'll take the limit of our difference quotient. So our f prime of x will be the limit as h approaches 0 of our f of x plus h minus f of x, which we obtained in step 2 all over h. Now to take our limit, we'll rationalize our numerator, which means we'll multiply numerator and denominator by the conjugate of our numerator. Next, we'll simplify. Now in the denominator, because we're trying to cancel out that h in the bottom, we are not going to distribute the h in. I want to keep that h out to make it easier to cancel. But in the numerator, because I'm trying to rationalize the numerator, I do want to FOIL that numerator out. Because we're multiplying by a conjugate using the difference of squares, and we get 4x plus 4h minus 1 minus the quantity of 4x minus 1. From there, we would simplify the numerator by distributing and canceling out like terms. Well, after we do, we would see that the 4x minus 1s would cancel, which would leave us with a numerator of 4h. Then we can see the h's cancel, which is what we want to see, which leaves us with us taking the limit as h approaches 0 of 4 over the square root of 4x plus 4h minus 1 plus the square root of 4x minus 1. Now we can use direct substitution by replacing h with 0. And when we do, we have 4 over the square root of 4x plus 4 times 0 minus 1 plus the square root of 4x minus 1. And when we simplify the denominator, we get 4 over 2 times the square root of 4x minus 1. Then we can reduce the 4 and the 2, and we get that f prime of x equals 2 over the square root of 4x minus 1. Now that we found our derivative, we can determine where f of x is differentiable. If we only consider the equation we got for f prime of x, we're tempted to say that the domain of f prime of x is 1/4 to infinity. This is because we need the 4x minus 1 to be strictly positive in order for the square root operation and the division to be defined. However, before we can conclude that that is indeed the true domain of f prime of x, we do need to consider where f of x has continuities. However, f prime of x does not have any discontinuities on its domain. Therefore, there is nothing that we have to exclude from the domain of f prime of x, and the true domain of f prime of x is 1/4 to infinity. Therefore, f of x will be differentiable on the interval 1/4 to infinity.